Hi, Michael.
Hey, Charles. Well, that was fun.
That was fun. We should do it again.
I don't think we need to do it again. I think we've now covered everything we wanted to say about reinforcement learning.
And I'm completely sure that we haven't.
Well, what haven't we covered?
Well, what haven't we covered?
Well, we covered TD lambda.
Sure. So we talked about TD lambda, we talked about a few algorithms here or there, but we haven't really touched on the big questions. We haven't covered everything that we should.
Like?
Burlap.
We have definitely covered burlap.
Okay, sure. There was a tutorial and there were assignments about it, but you haven't answered the big question about burlap.
Which is what?
Why burlap? Why do we need anything like burlap? Why don't you just use the UCI database and Weka? We're done.
Right, so the UCI data set, or the repository, and Weka are really great for supervised learning, but they're not actually well situated for reinforcement learning. Weka doesn't include reinforcement learning algorithms in it. The UCI repository doesn't include reinforcement learning problems in it. You really need a different setup for dealing with reinforcement learning problems.
You need a difference? Okay, I don't understand that. So we have algorithms. We've talked about many of them in class.
That's right.
So algorithms are algorithms are algorithms are algorithms. And this is all machine learning. And so all we need is data. And that's what repositories are for, data.
So, so burlap is trying to answer both of those issues. One of the things that burlap is trying to be is a collection of those algorithms are algorithms are algorithms are algorithms. And it's also providing kind of a replacement for data. So data in the reinforcement learning setting is really hard to work with. Instead, what burlap has is a set of simulators, the ability to act like the environment so that the learning algorithm can interact with it and learn from that.
Oh, I see. So the key word there is interact. So the notion in supervised learning is you've just got data. You've got input and output pairs, input and output pairs. But as we've pointed out multiple times, in reinforcement learning, it's not just about input and output. You, in fact, get to see states and rewards. You take actions. Those are the kinds of things that you do, and that requires interaction.
Right, and the data that you actually see depends on how you're exploring the environment. So just capturing a big static set of data and presenting that to the learner isn't really the reinforcement learning problem.
Okay, so I like that. So I heard two things there. One thing I like and one thing I don't like. The thing that I like is that you've distinguished reinforcement learning from supervised learning. You talked about the need for interaction and how that's sort of crucial, and you said your solution was having simulators.
Right, so I agree that that's not a great thing. So simulators are good in the sense that you can actually interact with them, and so it's a way of transferring an environment or a test problem from one research group to another research group.
Sounds good.
But on the bad side, they're not really data. It's not actual data coming from a problem, it's just fake.
Oh, so then you're suggesting, this is the second thing that I didn't think I liked, you're suggesting that we don't have any way to make reinforcement learning work in the real world.
It is more challenging, but it is not the case that reinforcement learning hasn't been used to solve some real problems.
Like what?
So it's worth probably mentioning a few of them. We talked about backgammon as part of the class, the TD gammon algorithm, that actually learned to play backgammon at a level comparable to, if not better than, human beings. There's other sorts of problems that are probably worth talking about as well. Elevator control is an interesting problem to think about from a reinforcement learning perspective.
How so? How is elevator control a reinforcement learning problem?
Elevator control, if you think about the elevators in a building, they're trying to work together to move people to where they want to go. And so we have actions, we have states, and we have rewards. The actions are where the elevators are trying to go, whether or not they're going to open their doors at a given floor. The states are what is the arrangement of all the different elevators at the moment, which floors have elevators on them, which don't.
Which buttons have been pressed?
Which buttons have been pressed, so who's waiting on which floors. And from the reward perspective, you can try to get the system to try to minimize wait time for people, right? So that's something that you can measure. How long is somebody waiting on the third floor for the elevator to come, and then eventually getting to the destination floor? And that's something you can measure and something that you can try to find ways of behaving to improve. Okay,
cool. So that's a reinforcement learning problem. I like that. Anything else?
Yeah, so that one actually was done in simulation.
Oh, okay.
But there has been some good work in reinforcement learning in robotics. So one that's maybe worth mentioning is the helicopter work.